quality of service. And that's the basic difference between the cellular spectrum as well as the your Wi-Fi service. Okay. So then recently there is another term which is being coined is the shared spectrum. So shared spectrum is in between the licensed and the unlicensed spectrum, and using the shared spectrum, you can have the unlicensed users, like free users, can access your license network and get the better quality of service. Because unlicensed spectrum, you are not guaranteed to get the good quality of service like in the Wi-Fi, but by using the shared spectrum, unlicensed users can get a better quality of service. On the other hand, from the licensed spectrum point of view, you know that for the licensed spectrum, you need to pay, and the spectrums are very expensive. So sometimes you can see that the licensed spectrum user or licensed user can be offloaded to the unlicensed spectrum so that they can use the lower cost spectrum or the free spectrum for transfer of their data. For example, in the LTE, you might have seen that the LTE plus Wi-Fi. So what happens here? When you have a good strong network, the LTE call gets diverted through the Wi-Fi spectrum. So this is called as the offloading from the licensed spectrum to the unlicensed or the shared spectrum, because you have the limited license spectrum, and with the high density of the user, there is a high probability of the call drop. So how can you reduce the call drop, or how you can
excuse me, sir.
Yeah.
Excuse me, sir. Sorry to disturb you. Just I needed your permission to record this your talk. Is it fine if we are
yeah, that is fine.
Okay, thank you, sir.
Yeah, just let me know if you're sharing over the public one.
Okay, sure, sir. Thank you.
Yeah. So license spectrum is always a paid spectrum, so it is a limited in accounts, limited in amount. So to support the large number of users, you need to weigh to see that how you can offload the users to the other one. So they have started in the LTE with the Wi-Fi as a offloading mechanism, and you will see that it will become more and more common in the 5G. So in the wireless network, you have the various type of users. You will say that you will have primary users or the user which are licensed users. For example, in the mobile network, when we buy the Airtel SIM or the Jio SIM, we are paying for on the monthly basis. So that means we are the licensed users. That means we have the access to the spectrum and we are paying for that spectrum. Then the secondary users are the unlicensed users. So these are the not present as such in a network, but these are the users who are not paying for any service or operators, but they are identifying the spectrum which is not being used and they're sending the data over that spectrum. Okay, so you can build an indoor communication network by using the secondary unlicensed user, but it is not yet legalized yet. And this sensing user, secondary user, you need to see that they don't interfere with the primary users. Okay, because primary users are the one who are paying for the spectrum, so they don't interfere with this. So they may need a sensing capability to see that whether user is present or not. So depending upon the complexity of the secondary users, they can have the sensing capability or they can be without sensing capability. For example, IoT users are the battery operated users. They have the limited power, so you can't have the additional hardware for the sensing. So this can be without sensing. They just transmit the data. So your spectrum is divided into the multiple channels, and for each user is assigned a particular channel. So for example, in the LTE, your channel bandwidth can be 1.5 gigahertz, 1.5 megahertz, 3 megahertz, up to 20 megahertz. In case of the 5G, this has increased to 100 megahertz in the sub 6 gigahertz, or it can go to the 400 megahertz in the millimeter wave spectrum. So each channel indicates what is the minimum bandwidth assigned to each user. So I hope I'm able to describe the things effectively, and you are able to follow my screen and the slides. Then you have the wireless user terminals. So these user terminals also can be of different type depending upon the services they provide. For example, these user terminals can be the narrowband terminals. That means they can transmit only over the narrowband frequency. For example, our GSM mobiles, they transmit only over the 200 kilohertz, while in case of the LTE, you can transmit over 200, while in case of the 5G, you can transmit over the 400 megahertz of bandwidth. So user terminals can be narrow band or wide band depending upon the services for which they have employed. They can transmit over the single band or multi-band. For example, in the LTE, we had the carrier aggregation. So you can have the multiple 220 megahertz transmission to get the maximum 100 megahertz transmission. So you can transmit over the multiple carrier frequencies simultaneously, while you can transmit over the smaller carrier frequency. They can be half duplex or full duplex. Half duplex means you can either transmit at the same time, or you can transmit or receive. You can't do both the things. In case of the full duplex, you can transmit as well as receive on the same frequency simultaneously. So depending upon the hardware availability, the cost available, you can build the different types of the user terminal. Similarly, you can divide this user terminal into different types based upon your different characteristics. I'll just keep this one. This is just for your information. And then last thing in your wireless network is the base station. So base station is nothing but your mobile towers, which will help us to communicate with the other users. So if I'm sitting here and I need to make a call someone else in some other university or some other room, my call gets directed to my destination via the base station. So the base station with infrastructure means the base station has a complete control over how the calls are being initiated and how the calls are being transmitted. For example, this is the license spectrum. So you can call this is the spectrum which is existed today, like in the 3G or in the LTE. This is how the base station looks like, where only the primary users are there, where primary users are the users which have purchased the SIM and which are paying to the service operators on the monthly basis. So you can see that in this case, the base station has to provide the data as well as control link to the primary user. That means base station needs to keep a track of whether each user is active or not. If the user wants to make a call, on which frequency it should be transmitted, on which bandwidth should be allocated, which frequency band it should be allocated to each other. So that is done over the control link. And over the data link, actual data is transmitted. For example, if you are making the voice call, your voice message gets converted into the set of binary data, and this data is then encoded, data modulated using the data link. But on the control link, you decide what modulation scheme to be used, what bandwidth to be used, what central carrier frequency to be used, whether to use the MIMO case, multiple antenna case, whether to use the transmit diversity, whether to use the multiplexing. All those things, decisions are taken by the control link. And who takes the decision? Taken by the base station. That means your service operator has a complete control over the communication. But what is the problem with this network is that it operates only over the license spectrum, and as the number of users increases, it becomes very difficult for the base station to manage those users, and then there is a probability of the call drops or the poor quality of service. So for example, if you see in the today's scenario, we prefer the we prefer the voice call over the WhatsApp instead of the voice call over the license or the LTE spectrum. And why this is happening? Because you have the very limited number of base station, because it's costly, and the quality number of users in India, especially in Asia, the user density is significantly large. So that's why the quality of service is poor, and that is the reason people are exploring the shared spectrum or the unlicensed spectrum. So in the shared spectrum, you can see that you have the primary users and you can have the secondary users. Now, who is the secondary users? This can be the secondary users which is using the Airtel spectrum, but he is paying for the Reliance Jio. But since he is using the shared spectrum, for that particular call, he may not have to pay for that spectrum. So the secondary users are the free users. They are not paying it, but they are trying to make use of the spectrum here. So you can see that in the shared spectrum and with the base station with the infrastructure, base station not only has to provide the support for your primary users, but also for the secondary users. And you can see that this is not at all feasible, because base station itself is struggling with the licensed user. And when you go to the shared spectrum, the load on the base station has significantly increased. So in case of the unlicensed spectrum also, you can see that in case of the with infrastructure, base station has to provide the complete support. So this is the ideal case where the base station has the complete control over the network in the shared, unlicensed and the licensed spectrum. But it is not feasible because base station cannot handle so many users and so many requests from the multiple users. So then there is a concept of the base station without infrastructure is being explored. What does this means? In this case, base station compared to the previous one, base station does not provide any control link. Base station only provides the data link. So base station will receive the data from the user. If the data is received correctly, it will transmit the data to the next user. If the data is not received correctly, that data will get corrupted. So this is called as a base station without the infrastructure. You can see that we are able to reduce the load on the base station significantly, but this is not a practical solution, because you know that the probability of your call gets through will be very less, because there will be so many users trying to communicate and there will be so many collisions between the users. So we need to come up with the somewhere between the with or the without the infrastructure. So this is not possible in the license spectrum. It may be possible in the license spectrum because we don't worry about the quality of service. So it may be possible. So in the 5G, they are trying to see how we can optimize the control link and how we can provide the better experience to the user, but without increasing the loads on the base station. So the aim is that for the primary user, for the users which are being paid, the control link will be provided. So they will get every information and they will get guaranteed quality of service for the primary user. But for the secondary user, there won't be any control link. Again, in this case, what it may happen that the secondary, there will be no motivation for the secondary users to use the license or the shared or unlicensed spectrum, because he will always get the poorer quality of service. So the next version is that there will be a control link for the secondary user. So it will be getting some quality of service, but the priority will be with the primary user. So secondary user will get certain support for the base station when it is available, but the priority for the will be given to the primary user. So there are multiple things are being explored in the 5G, and again, this will not be a part of the 5G. Hopefully, after the 5G is properly installed and if it is started working, then these things might be introduced in the subsequent one. But if you look at this overall idea, you will see that there is a certain research challenge to be solved here, because you can see that base station needs to cater the two types of the users, and base station needs to allocate the resources to your primary users as well as the secondary users. And in some cases, since the limited support is available to the secondary user might have to search the resources on its own so that it gets a better quality of service. So that these are the research problems are there where we can make use of the where we can make use of our machine learning or the AI ML algorithms. Okay, so any doubt? Anyone has any doubts or any questions, so that I can stop? I can take a break of say 30 seconds and then start explaining the how the industry or the academia is solving this problem. Any question?
Any participants, if any query you are having
Yeah.
till now, you can please ask the question.
Okay. So if there are no question, is there any question? No.
No, sir,
Okay.
I don't think so.
Okay.
You can
Okay. Yeah. So if there are no questions, so let's start with the discussing the problem statement and what are the issues are there. Okay. So before we go into the problem statement, I just want to give you the some details about the how our cellular networks work. Hello. Yeah. Can you
Someone
please
has
mute your mic?
Ankita, please mute yourself. Okay, sure.
Okay. So usually in the cellular spectrum, you have the different data channels and different control channels. So this slide just give you the idea about the what are the data channels and what are the control channels. So if you read the 3GPP standards, you will see that there people talk about the PDSCH, PDCCH, and all this one. So these are nothing but the control and data channels which I discussed before. So the data control channels we can solve as the physical downlink control channels. So this is physical downlink means from the base station to the user. So an uplink means from the user to the base station. So downlink control channels, where the base station tells the user that which channels to be used, which frequency and bandwidth or modulation scheme, coding scheme, beamforming to be used. And the data channel is where the actual data is transmitted. And what we are talking about here is that base station provides the data and control channels only to the primary users, while the secondary users needs to find out their own resources without any central coordination. That means there is no support from the base station, and this is called as a distributed learning. So that's where the term about the distributed learning has come up. So there has been a lot of research study experiments have been done by the industry as well as academia to see that whether there is actually a need of the AI, machine learning, deep learning in the wireless network, or especially when you consider the problem of the resource allocation. For example, DARPA is the one of the research wing of the US government, and they float the different challenges every year, and where the university or the university students, research labs participate. So in 2016 and 2018, they floated this Spectrum Collaboration Challenge to see that how the AI ML algorithms can be used for the resource allocation in the wireless network. So you can look at their website to know more about the details about this AI ML. And one thing which they learned from this challenge, after 2016, they started another challenge in 2018. And after various competition and after studying the various data, they came to the conclusion that various demonstration in the challenges have shown that the autonomous radios means a radio which can take the decision on their own, like secondary users, can manage the resources better than humans, like better than using the base stations and controlled by the service operators. If we develop the radios which are powerful enough with the intelligence, they can manage the spectrum, they can make use of the spectrum better than the humans. So that means AI will rule the wireless spectrum. So if you want to do the resource allocation in the future networks, you should make use of the AI. If you want to learn more about it or read about it, there is a paper in the IEEE Spectrum in 2019. It's very good magazine paper. It is the Spectrum, which the paper titles is the AI will rule the airwaves, and it's a very important paper if you are working in this AI ML for the wireless communication. So you should look at this Spectrum. So I just want to share the few highlights again from this paper. So one of the paper highlights from this paper was that ultimately it is easiest to treat the resource management, like allocation of the spectrum, allocation of the time, frequency, bandwidth. It can be considered as a reinforcement learning problem. It's a machine learning problem in which we reward the AI algorithm. We reward the algorithm. That is, algorithm takes the decision. It tells the user that which channels to use, what bandwidth to transmit. And if the transmission is successfully, we send the reward to the algorithm that you have succeeded, and we penalize the algorithm when it fails. So this is the concept of the AI algorithm. For example, AI may receive the 1 point for successfully transmitting the data and lose 1 point for the transmission that was dropped. And over the time, once you keep on getting the rewards, the algorithms will learn, and then it will try to get the best decisions. So by accumulating the points during the training period, AI remembers the successes and tries to repeat them, while also moving away from the unsuccessful time. So the hope is that over the time, your algorithm will learn the RF spectrum environment, how the other users are behaving, and then try to gain the as much throughput as possible. So this was the initial observation from this study. Another observation is that now in your network, you don't have a single users, you have the multiple users. So you can't have the multiple users which are independently trained. You need to make sure that all the users are trained collectively. So for example, imagine playing a game of cricket where you have formed a team with the people you have not met before. So you don't know any skill set of the people you are playing with. So in that case, your team's ability to play together is not going to be anywhere near as good as the teammates who have been trained together for years. So if you are going for a cricket match and if you form a team where you don't know any members of your team, their skill set, then your ability to perform may not be as good as the teammates who have been playing together for the multiple years. So that means here we need to make sure that the multiple users in the networks, they know each other and they know how the others are taking the decision, so that they avoid the competition and they improve the collaboration. So to date, the most successful challenges involving the multiple players or multiple users has been where the AI have been successfully trained. So when the AI of the multiple users are trained together, then only you will get the better throughput. So AI in the distributed multiple scenario is challenging, because now you have the network where you have the multiple users. The users can coming and going at any times. Their services are different. Some can be IoT users, some can be ADAS users, some can be wireless users. So that's a very challenging problem. Another challenging problem is to predict the availability of the resources. Your spectrum is changing with time. It is dynamically changing. Your SNR, your environmental condition, your speed of the vehicle, these are changing with the time. So you need to predict what is the availability and the quality of the resources. So if you predict well, if you use the more process prediction, it will help the collaborating radio to capitalize on the every opportunity to transmit the more data. So if you do the deep learning, machine learning algorithms to predict the spectrum in the future, you will be able to utilize the spectrum more efficiently without competing among the users. Hopefully, the next generation AI can learn to predict the resource availability with enough precision to not to let a single unit go to waste. Okay, so this is the challenge in the research one, and people are looking forward to the AI ML algorithms to solve this challenge in this domain. Now, the one which I discussed is all about the academia. But what about the industry? Is the industry is also looking at the AI/ML as a possible solution? So I'm giving you this recent slide. It is from the July 2021. That is 3-4 months back. And if you are working in the wireless domain, we know that the 3GPP is the one committee where all the standards of the 5G, 3G, 4G, 5G have been defined. And from the June onwards, they have started the discussion about the how the AI MLs can be used in the wireless network. They have started with the wireless physical layer, but similar discussions are also going on the MAC and the upper layer. So these are the slides which are presented recently, and you can see that the industries are also looking for the how the AI ML can be exploited for the improving the performance of the wireless layer. So if you are working in this domain, this is a very good chance to see that to take this as one of the research problem. For example, if you take the wireless physical layer, what is the physical layer where every your channel encoding, data modulation, beam forming, OFDM, and the RF signal processing transmission over the carrier frequency takes place. That is what the physical layer. And what people are currently are working about, how you can improve the performance of the each block. You have the different block, how you can improve the performance of the different blocks using the AI ML algorithm. So that is what the currently people are working on. In the future, you will see that the people will replace all these blocks using the single AI ML algorithm. You can see that entire receiver can be replaced by the single AI ML algorithm. Again, there are, if you look at into the IEEE Spectrum and IEEE Communication magazines, there is a couple of very good papers on the making the AI ready, making the radio intelligent. So you should look at this one. So this is what the industry is also now looking at. This is the slides I have took it from the industry presentation which happened in June. And this is what the timeline you can look at. So you can see that if you look at the timeline, whatever the enhancement will happen at the wireless network, which will include the ML1, will happen from 2022, 2023 onwards. So you can see that at least we have almost 1.5 years to take this as a research problem, and then over the years contribute in this domain. But there is a one catch. So if you want your work to be useful or impactful, first thing you need to make sure that you understand the 3GPP specification. You don't make any undue assumption which is not as per the standards. So that's why understanding the standards, understanding the various assumptions you are making in your things is important. And second thing is that you need to make sure that whatever you do, you need to test it in the real world environment. You need to test it in the real RF environment. So you need to develop the prototype. So as long as you meet these things, you will be able to contribute significantly in this AI/ML for the wireless domain. So with this, I hope I have motivated you enough for the why the AI/ML is important in the wireless network. So now what I'll do is that I'll take the 1 minute break. I'll see that if there are any questions from your things. Otherwise, I'll take the 1 minute break and I'll come back to you after 1 minute, and then we'll start about the some of the solutions for the AI/ML for the wireless one. So if you have any question, feel free to ask me now. Otherwise, if you want to take a break, water break or washroom break, we'll come back to this next part in the 1 minute. Any questions? Okay, so if there are no questions, so I hope please take a break. So because in the online environment, 2 hour lecture is a very difficult thing. So I usually prefer a break of 1 minute after half an hour. Okay, so let's get started. So as I told you that there are AI/ML algorithms. There are people are looking at the AI/ML algorithm as one of the solution to improve the performance. There are some issues regarding the performance of the AI/ML algorithms in the real world environment. Also, the feasibility of the AI/ML algorithm, because these are the complex algorithms. So if you try to implement with the radio, the overall area and power consumption will be huge. So a lot of issues are there. So you need to tackle these issues one by one. So in this talk, I'll discuss about how this distributed learning algorithms can be used for the resource allocation, which I have discussed in the beginning for the wireless network. I'll start with the single player setting. I'll discuss the single player setting in more detail. And then I'll discuss the introduction to the multiple player setting, but I won't discuss the multiple player settings in more detail because I believe the Rohit will talk about it in his talk later. So I'll keep that topic for him because he has worked during his PhD. So I'll focus on the single player setting and I'll introduce you to the research problem in this. So So again, assuming that we have one wireless network and we have the multiple primary users and we have the one single secondary users. Okay, we have started with a very simple settings. We have multiple primary users and the one single secondary users. So we consider the infrastructure less network for the secondary users. That means secondary user has to find its own resources. He or secondary users needs to identify their own resources. The communication is time slotted. That means you do the communication in a time slot. In every time slot, you identify the frequency spectrum over which you are going to transmit. You transmit. At the end, you get the feedback like what is the BER or throughput you have achieved, or whether the transmission is successful or not. We assume that there is one user, and we assume that there are total K channels are there. So that means if I am a secondary user, I need to identify which of the K channels I need to use or transmit on. I can select only one channel at a time because that's why I have used the narrow band user. And I have considered the type 2 one, which I have discussed in that table. That means I can either sense the spectrum or I can transmit the spectrum. I can't do both. Okay. So depending upon the type of your radio, you need to develop the different algorithm. And all the K channels are different. That means on each channels you may get the different throughput. So that means ideally you should select the channel which will provide you the as high throughput as possible. Okay, so this is the time slotted communication. In every time slot, user select the channel, then it will sense the channel. It will check whether the primary user is present or not. So you can use any sensing algorithm. Then it will transmit over the channel, and at the end you will get the feedback. Feedback can be success or failure, or it can be in terms of the how much throughput you got. So it can be Bernoulli feedback 1 or 0, or it can be Gaussian feedback, which is with the particular distribution. And what is my goal? I need to maximize the expected sum rate, or I need to maximize the what is the throughput, expected throughput I got. So what the simple strategy will be, I have the K channels. I'll select the top channel, the channel which I choose, which provides the highest throughput. But the problem is that I don't know the channel statistics. So I don't know what is the throughput provided by the each channel. So I need to learn the channels. Okay, so that is my challenge here. So to mathematically formulate the problem, you have the K channels with the distribution Vk, and the mean is mu K. So that means with every channels, I'll get the throughput with the mean mu K. So this mu K may be different for each channel. For example, I can consider the 3 channels with 0.1, 0.2, and 0.6. So you can see that the throughput on this channel is around 0.1 Mbps, throughput on this channel is 0.2 Mbps, throughput on this channel with 0.6 Mbps, and there will be certain variance. So ideally, what should I do? I should select this channel as often as possible. But the thing is, I don't know this value, so I need to learn these values. That's the challenge. So if I see the select the channel K in the round T, that means if I select the channel K, then I'll get the throughput X of KT from the distribution of that channel mu K. Okay, we can see that each sample is independent across time and arm, so this will help us for the analysis purpose. And how you select the channel? So I have the K channels. So which strategy or which policy I should use to select one of the channel? So that policy we can call it as a IT as a policy. So using this policy or using this algorithm, I select the channel in each time slot. And this policy, how it selects the channel, it will select the channel based upon the past observation. Like in the past, which channels I have been selected, what was the throughput I got, and based upon that, I will select the channel in the current time slot. So what is my expected regret? So this is the performance metric. So suppose that I have the 3 channel, which is the expected throughput as 0.1, 0.2, and 0.6. So if I tell you in the beginning that this is my expected throughput, what you will do? You will select these channels all the time. Okay, so this is the maximum throughput you can get. So you can see that T is the number of time slot, and the mu I is the maximum throughput. So this is the 0.6. So this is the, suppose T we take it as 100. So you are running for the 100 time slot, and in every time slot you select the channel with this throughput. So what I'm going to get, my expected throughput is 60, and this is nothing but the maximum I can get. But since you don't know the channels, you need to select all these channels sufficient number of times so that you can get to know that, okay, this is the channel. So in that case, your expected throughput will always be less than this 60, and this is the expected throughput. You can see that it is the expected value of the mu of the channel which you have selected in the each time slot. So you are doing the sum of that one, and the difference between the one where which you can do the best, which is 60, and the one which you have actually achieved using the algorithm is called the regret. And ideally, your regret should be as less as possible, because you need to make sure that you do well as your algorithm which knows all the mu values, okay, which is this algorithm. So you want to minimize the difference between your optimal algorithms and the algorithms which is developed by you. Okay, so here again, these are the multi-arm bandwidth algorithm. So usually I use the term sometimes arm or the channels, which is the same thing. Okay, so we can use the same term for the both the things. So now I would like you to tell me how you can solve the problem. So before I can, we can take the solution from your end. So let's play a very simple game. I need a one volunteer from your end. Can you take anyone? Can you volunteer for this game? Anyone wants to participate in this game? Only one person I need.
Anyone who would like to volunteer?
Yes.
Oh.
I hope everybody is not sleeping. It's a cold weather.
Yes, sir.
So who is
Okay,
there?
so we have
Name
Neetu is
Neetu
there, right?
Ahirwar, right? Okay,
Okay,
Neetu,
Yes,
okay,
sir.
you can. Yeah.
okay,
Good
good.
morning, sir.
Good morning. So good. So one person is awake other than Rohit. So Neetu, so there is a challenge for you. So you have the three
Yes, sir.
channels.
Yes, sir.
In every channel, you need to select. In every time, you have the 10 time slot, and you have to select one channels in every time slot. And once you select the
Mm,
channel, I'll tell you how much throughput you will get. And your aim is
mm,
that at the end of the 10th time slot, you need to tell me which channel is the best in terms of the throughput. Is the
yes, sir.
problem
Sir,
statement is
pardon,
clear?
sir. Yes, sir.
Yeah,
Pardon, sir.
yeah. Okay, can we start now?
Sir, she is requesting to give the again problem
Okay,
statement.
okay,
Give
okay,
the again
okay.
problem
So
statement.
Yes,
you
sir.
have the
Yes,
three,
please.
you have three channels to select. Channel 1,
Yes,
channel
sir.
2, channel 3. You can select
Yes,
only
sir.
one channel at a time,
Yes, sir.
and you have the 10 attempts. So in every time slot, you will select one channel. I'll give you the, once you select the channel, I'll give you the throughput you have got. And at the end
Okay,
of
sir.
the 10 channels, you need to tell me
Yes,
which
sir.
one is the best in terms of the throughput.
Yes, sir. Okay, sir.
So let's start with the first time slot, which channel you will select. And I have the
Channel 2.
already written the throughput. So I'm not
Yes, sir.
changing the throughput based upon this. So channel 2, you have selected the channel 2 in the first time slot, you got the throughput 1. So throughputs are either 0
Okay,
or
sir.
1. Okay. So
Okay,
in
sir.
the
Okay,
second
sir.
time slot, which you will select?
3.
3. Okay. You also got
Yes, sir.
1 in the second time slot. Then
Okay, sir. Then channel 1.
channel 1. Channel 1, you got 0.
Okay, sir. Then channel 3.
Channel 3. So we are in the 4 time slot. You got 0.
Okay, sir. Then channel 2.
Channel 2, you got 1.
Yes, sir. Channel 1.
Channel 1, you got 0.
Okay, channel 2.
Channel 2, you got 1.
Okay, sir. Then channel 3.
Channel 3, you got 0.
Okay, sir. Channel 9. Channel 1.
Channel 1, you got 0.
Okay, sir. Channel 2.
You got 1.
Okay, sir.
So which one is the best channel among this one?
Best channel is channel 2.
Channel 2. Okay.
Yes.
And so how you solve this problem? Like what are the issues you face while selecting the channel? Like how you were selecting the channel? What strategy you use?
Sir, I randomly picked the channel.
Okay, you randomly picked this. Okay, good. Okay, thanks,
Yes,
thanks.
sir.
So you can see that you
Okay,
don't
thank
know
you, sir.
the three channels, and you need to take a decision, or you need to select the channels, and you need to learn from your past observation. So when you are selecting the channel 10, you are learning from the past observation that this guy is doing better, so I'll select the channel. So this is nothing but you need to learn from the history, and you need to select the channel. And you can see that this is the exploitation trade-off. You need to explore the channels, all the channels, so that you learn from that, but you need to exploit the best channel. You need to select the best channel as much time as possible so that you get the better throughput. And just for your information, the channel 1 has the throughput of 0.2, channel 2 has the throughput of 0.7, and channel 3 has the throughput of as 0.4. So if out of 10, if you have selected the channel 2 all the time, you would have got the throughput of 7. But since you were not aware about which channel is good, so you have to select the other channels, and you got the throughput of 1, 2, 3, 4, 5. and your regret is nothing but the 7 minus 2, that is the 7 minus 5, that is the 2. So this is the regret you have incurred because you are not aware about the channel, and this is the regret of the learning algorithm. I hope these concepts are clear to you. Okay. Any doubt?
Yes.
Any question? Anyone else? Any question? So you can see that when you are considering the single player case, we can consider the multiple policies. For example, one policy is that I can select the each channels t by k times. For example, I can select the all the channels uniformly. That means I can explore the all the channels in the uniform manner. Okay, so that can be the policy. So there is a one question about the good regret. That what is the regret? So regret is nothing but the. So if you look at this one, regret is nothing but the. Suppose that you have the channel 1, channel 2, channel 3 here, right? If I tell you in the beginning that the channel 2 has the throughput of 0.7, that means you would have selected the channel 2 all the time and you would have got the the reward of 7. But since you are not aware about this channel, you need to explore this one and you got the reward of this one. So the regret is nothing but the difference between the performance of your optimal algorithm. Optimal algorithm is the one which knows everything about the which channel is good. So that is what the this one. You can see that here I am selecting the best channel all the time, and this one is the performance of your algorithm, where you have to explore the other algorithm, other channels. So difference between the two is called as the regret. Is this clear, Abhiranjan? Okay, so you can see that in the single player case, I can follow the policy where I can explore each channel same number of time, but you know that that is not a good policy. I can exploit the best channel only. For example, in the beginning, I will choose that the channel which I got the highest reward, and I will keep on using the channel. For example, if you go back to here, here you can see that the Neetu had the option of selecting this one or this one all the time. So instead of exploring this one, at this point, she could have selected this channel all the time. But you can see that this may work if she would have selected the channel 2, but it would have, if this may fail if she would have selected the channel 3. So if you don't explore enough, if you directly exploit the channel, sometimes it may work, but sometimes it may not work. And the policy is that you first explore for certain time, for say epsilon time, and then exploit. So there are multiple policies are there. We will see the difference between the each policy. But what is the final understanding is that too much exploration. That means if you explore all the channels for a long time, it may not be good. Or premature exploitation, that you without exploring, without learning about the channel, you start selecting a one particular, you focus on only one particular channel, is also not good. Okay, so you need to have the good balance between the exploration and exploitation. You should not explore too much and you should not exploit too much. For example, suppose that I have the 5 channels. The each channel is the has the throughput with this through one, and I'm running it for this 10,000 time slot. So which is the best channel here? Can someone tell me which is the best channel here among the channels which I have shown?
Sir, mu4.
Okay, mu4 is the best channel. So your optimal algorithm is the one which will select the mu4 all the time. So what is your optimal throughput? Throughput will be 10,000 into the average of 0.8. So you will get the maximum throughput, you will get the 8,000. But the problem is that if I don't give you this information, you have to explore all the channels sufficient times to know that the mu4 is the best channel. And this is called as a penalty due to the exploration. So you can see that I have run the algorithm for the different setting. This is the throughput or the reward I got. Reward or the throughput are the same terms. And you can see that the optimal policy, which knows that the mu4 is the best one, it will get around 8,000 as a reward or throughput. But This is the optimal policy. It already have the prior knowledge, but since you are developing the algorithms or you are running the algorithm, you don't have the prior knowledge. So you need to do the exploitation or exploration. So in this algorithm here, you can see that I am doing the exploitation only. What do you mean by exploitation only? Here I am doing the exploitation. That means in the beginning, I'll select the which channel has got me the highest reward, and I'll fix to that channel. So it most probably what is happening here, I am instead of fixing it to the mu4, I am locked to the mu3 channel because mu3 worked well in the beginning, and because of this, my performance is very poor. So this is the problem where you do the less exploration and more exploitation. Here you can see that by changing the epsilon, the probability of the exploration, you can see that by changing the epsilon, I get the different performance, and which is always better than the complete exploitation. So what does this say? You need to do certain exploration. You need to look around all the channels, learn about this one, and then exploit the channel. Okay. So basically, you need to develop the algorithms which will explore sufficient number of time and then exploit. But the algorithm should not explore too much, and algorithm should not exploit too early. And this is the challenge of the design of the multi-arm bandit algorithm. Is this problem statement clear? Any doubt? Any question? Okay. Okay. So if this is the problem, again, this is a well-known problem. This has been discussed multiple times in the machine learning community. And what is the best you can do? Like, what is the best you can achieve? So there is a lower bound has been provided. So here I'm just using few terms. So mu star is the one which indicates that which is the best channel. I star indicates the corresponding index of the best channel. Okay. Delta I indicates the difference between the best channels and the ith channel. For example, suppose I have three channels, 0.1, 0.2, 0.4. Then my mu star will be 0.4. I star will be 3. That is the third channel. Delta I for the first channel, it will be 0.4 minus 0.1. That is 0.3. For the second channel, it will be 0.2. And for third channel, it will be 0. That is mu star minus mu I. Okay. Delta means minimum value of the delta I. So minimum value of the delta I is the without including the base channel. So the minimum value between the 0.3 and 0.2, that is the 0.2. And the mu values are the 0.1, 0.2, 0.4. So these are some notations I'm using. So there is a lower bound on the what is the minimum regret you have to incur. Okay. Again, it was proposed in 1985. And you can see that you don't need to worry about this one, but you can see that the lower bound depends upon the difference between the UI and the U star. For example, when I consider this problem, 0.1, 0.2, 0.5, 0.1, 0.3, 0.5, and if I consider another problem of 0.1, 0.2, 0.3, you can see that this problem is difficult to learn than this problem. Because here the arms or channels are very close to each other. Here the arms and channels are very away from each other. So this problem is easy. So that means the lower regret will be less compared to this problem. Okay. So what this bound says that anyone who will develop the algorithms for this multi-arm bandit single player case, you cannot have the algorithms which offer the regret lower than this one. So basically, when you will develop the algorithms, you need to show that your regret, you will be guaranteed that your regret is higher than this one, but you need to show that how your regret is as close to this one, which is the optimal regret as possible. But in this thing, you can see that your values depends upon the corresponding problem, like mu values. Okay. So there is another algorithm, another proof in 2006, where it is the independent, problem independent. That means it doesn't depends upon the mu value. And here it says that the minimum regret of your algorithm will be there. So what it is saying, if you develop the algorithm, I'll be able to come up with any mu value which will make sure that your algorithm will incur at least this much regret. You cannot have the regret which is less than this value. Okay. So these are the minimum bound is there, and then your task is that how to solve this problem, like how to develop the algorithms which will minimize the regret. So any idea, anyone has any idea? Suppose this problem is given to you, how you will come up with the algorithm which will solve this problem? Any suggestion or any idea? Because research work is nothing but identifying the problem. The identifying the solution is very easy, but you need to come up with how you can identify the problem statement. So I have done the many important task of identifying the problem. You need to provide me the solution. Yeah, so the end idea is to minimize the regret, but how you will develop the algorithms? Can you come up with the algorithms to reduce this regret? Okay. So again, this is the one of the fascinating problem, and there has been a multiple solutions. So because of the sake of time, I'll discuss the few solution, and then I'll go to the next set of slide. So the one algorithm is that explore and then commit. Okay. So what does this mean? That means initially I'll select all the channels sequentially certain number of times. Then at the end of my exploration phase, I'll find out which channel is doing the better, and then I'll lock onto that channels at the rest of the time. So you can see that the M indicates that how many times I'll select each channels in the beginning. Then you can see that in the beginning, if there are till mk time slot, because there are k channels and each channel needs to be selected m times. So till the mk time slot, I'll select the each channels in the round robin fashion. Then after the mk time slot, I'll find out which channel is the best one till the time mk, and then I'll lock onto that channel for the rest of the time slot. And how I'll select which channel is best? Basically, it is nothing but the total reward I have got over that channel divided by the total number of times I have selected the channel. So that is called as the expected mean or empirical estimate of that channel. Okay. So what I'll do, I'll select the each channels m number of times in the beginning. I'll get the reward in every time slot. Then I'll divide that reward by the number of time slot I have selected the channels. And then at the end of my time slot mk, I'll find out which channel is best, and then I'll select that channel for the rest of the time slot. And then they have proved that the regret of this algorithm is less than this one. You can see that the lower bound has already been proven by the previous slide. So anyone who develops the algorithm need to find out what is the upper bound of your algorithm and how this upper bound is closer to the lower bound which has been given in the previous slide. Okay. So you can see that this is very easy to understand. In the beginning, you can see that you are selecting each arm mk times of 1. That means you are selecting out of this mk time slot, you are selecting your optimal arms only m time slot. Rest of the time slot, m minus 1 k time slot, you are selecting the suboptimal arm. And so you will incur the regret there. And then in case there will be probability that if you don't choose the arm correctly in this one, you will lock on the suboptimal arm in the rest of the time. And this is the regret because of that. And once, since M is the input from this user, you can calculate by solving this optimization problem, you can find out the M, and you can see that the regret is sublinear regret. Okay, it's not linear regret, it's a sublinear regret. So that algorithm is quite good. Okay, so this is the very simple algorithm, but you can see that the regret is quite high in this one. So can you do better than this? Okay, so that is one approach. The second approach is the optimism in the face of uncertainty, and this is how our human also behaves. Like, for example, when someone gives us something to, like for example, during the exam, we may have certain idea about the particular answer to the particular question, but what we do, we assume that okay, this with certain probability this answer is correct, and we try to submit that particular answer. Okay, that answer may not be correct or may not be wrong, but we have certain confidence. Okay, based upon my previous knowledge, this answer will be the correct, and we support that one. The same thing is happen in this optimism in the face of the uncertainty, because here you don't have the complete knowledge about each channel. You have certain knowledge based upon your past observation, and you try to be more optimistic. For example, for every channel, based upon your past reward, you find out the lower bound as well as the upper bound. So this is the mean, and you find out the lower bound and upper bound. Okay, and then you try to select the channel which has the highest upper bound. You can see that the each channel has the different upper bound based upon your past observation, and then among the channel which has the highest upper bound, that is the channel which has the highest probability of the higher throughput, you will select that channel. Okay, and this is called as the optimism in the face of uncertainty. So how this UCB, upper confidence bound algorithm works? This is the most popular algorithm in the today. So you can see that in this algorithm, in the beginning, you select the each arms once. So you can see that in the first k time slot, you select the each arm once. Then at the every time slot, you find out the upper confidence bound. So what is this upper confidence bound? You can see that there is this mean value, which is the expected mean value plus something. So you can see that this is the mean value, which is the learn mean value, and plus this is exploration factor. And this exploration factor indicate the how much uncertainty I have about this one. And you can see that there is a bottom is the number of times I have selected this channel. So if I have selected these channels only fewer number of times, what does this mean? I don't have much knowledge about this channel, so I need to explore this channel more. If I have selected this channel large number of times, that means I have sufficient information about this channel, so I can reduce my exploration. So using this term, you find out the index for every channel, and using this optimism in the face of uncertainty, you find out there is a max term here. You find out the channel which has the maximum upper confidence bound, and you select that channel, and you continue in this in the every time slot. And for this, you can see that the regret it is in terms of the log t compared to the square root t, and this is much better than the previous case. And you know that the optimum regret is kt, and here you can see that it is multiplied by the log t factor. So it is higher than the optimal one, but still it is a sublinear regret. So that means it is a good algorithm. So similarly, there are other algorithms also, UCB, KLUCB, Thompson sampling. Multiple algorithms are there. Because of the limited time, I am not going to discuss the other algorithm. But what I am going to show you the some of the simulation which says that how this algorithm works. And you will see that in the practical setting, the KLUCB is the very good algorithm, and Thompson sampling is also one of the popular algorithms. For your information, this Thompson sampling algorithm was developed in 1933, and it is based upon the Bayesian principle. And if you want to know more, you can contact me for the papers related to this one. And it performs very well in the practical environment. Even in the Yahoo search engine around in the 1990s, they have used the Thompson sampling for their search engine website application. Okay, so this is one of the popular algorithm, and you can see that over the time how each channel is being selected, and you can see that here the optimal channel is 0.5, and this has been selected higher number of times in each of the one case. So you can see that all the algorithms, UCB, KLUCB, and Thompson sampling algorithms, they are able to identify the best channel. So that is a good thing. But you can see that the Thompson sampling algorithm is better in terms of the exploration and exploitation trade-off. What does this mean? It is able to identify the optimal arms as quickly as possible, and that's why it is able to select the optimal arms 1843 times out of the 2000 time slot compared to the other algorithms. So you can see that this algorithm offers the lower regret. And how this algorithm works, they over the time they try to find out the confidence around their optimal means, and you can see that as these algorithms they try to optimize the confidence mean, and then they select the algorithm which has the highest confidence. Okay, so this is how the single user can, by using the this multi-arm bandit algorithms, can identify the best channels in the wireless case. Okay. Any question? Any queries regarding the regarding this single player multi-arm bandit algorithm? Okay. So if there is no query, so I can go ahead. So to compare the algorithm, because these are the most popular single player algorithm, you can see that the UCB algorithm is a very easy to implement. It's a very simple algorithm. But if you look at the equation of the UCB algorithm, there is a parameter alpha, which is the tuning parameter, and that needs to be set quite carefully. Then you can see that there is a KL-UCB algorithm, which is the one of the best algorithm, asymptotically optimal algorithm. It has a good performance. It performs better than the UCB, but it is very complex algorithm. I'll show you some of the results on the hardware. It is very complex algorithm. And then the Thompson sampling algorithm is there, which is one of the best algorithm. It is a Bayesian algorithm, one of the best algorithm, good performance in the practical application. But again, hardware implementation is a issue, and also it depends upon your distribution. So if you have the Bernoulli distribution, it will have the different algorithm. If you have the binomial distribution, if you have the Gaussian, if you have the exponential distribution, you will need to use the different version of the Thompson sampling algorithm. So that is the difficulty in the Thompson sampling. In case of the UCB and KL-UCB, they are independent of the distribution. You can use the same algorithm for the different distribution, but in case of the Thompson sampling algorithm, you need to use the different version of the Thompson sampling algorithm for the different distribution. But in the research world, just developing the algorithm, running the simulations is not sufficient. If you want to make the impactful contribution, along with your algorithm design, you need to do the performance analysis, and you need to test these algorithms on the hardware. So in our labs, we have already implemented the algorithms on the hardware. So I'll just go back to the, sorry for this one. Yeah, so you can see that in our lab, we have implemented this on the Zinc system on chip. So this Zinc system on chip has the ARM processor, which is the dual core processor, as well as FPGA. And via hardware software co-design, we have implemented this algorithm. And we have implemented the reconfigurable version of this algorithm. That means this architecture can be able to switch between the UCB algorithm, a different version of the UCB algorithm, as well as in the initial we have implemented the KL-UCB algorithm. And as I told you that the KL-UCB algorithm is a very complex algorithm, but it performs better than the UCB algorithm. So if you look at this line and this line, this is the execution time. You can see that the your UCB algorithms take only 792 microseconds for the 10,000 time slot, while the KL-UCB takes the 30,000 microseconds. So you can see that the KL-UCB is very good in terms of the reward. It will offer you the better reward than the UCB, but it is not feasible in the practical environment because of the very high complexity. So this is the one where we implemented on the FPGA. This is the one where you implemented on the ARM processor, and this is the one where you implement on the ARM processor. Plus, we use the Neon as a SIMD. That is a single instruction multiple data coprocessor, and we have tested this on the hardware. So the problem with the KL-UCB, you can see that it performs very well in terms of the reward, but you can see that it's very slow and it takes a lot of time. So what we did, we came up with the reconfigurable version of the KL-UCB, where what we did in the beginning, we used the UCB, and after in the beginning, we used the KL-UCB, where it will be able to identify the best arm quickly. And then in the hardware, you can see that we are able to switch between the KL-UCB in the hardware from the KL-UCB to the UCB. What it happens that your execution time has significantly gone down by 10 factor. You got the reward as close to as the KL-UCB, and your power consumption has also gone down, because you can see that after initial period, we are replacing the KL-UCB in the hardware with the UCB. So your power consumption has gone down. So that is the advantage of this reconfigurable architecture. Another advantage of the KL-UCB, conventional KL-UCB and our KL-UCB and the UCB combination is that you get the higher throughput. Obviously, KL-UCB performs better than the KL-UCB plus UCB because it has the better, it's an optimal algorithm. So you can see that in terms of the data bits, it performs better. But when you consider the throughput, which is nothing but the data bits and the time taken to transmit the data, you can see that the KL-UCB has a very high time to transmit the data, while the KL-UCB plus UCB takes very less time. So you can see that the throughput is significantly higher in case of the KL-UCB plus UCB than the KL-UCB. And in the wireless communication, throughput is more important than the UCB. So this was the initial work from our group on the realization of this algorithms on the hardware. Now you can see that here we have discussed about the KLUCB, UCB, but we have not discussed about the Thompson sampling. Because the Thompson sampling is a very complex algorithm, it uses the beta distribution. So it is a very difficult algorithms to implement on the hardware. So it took almost 1.5 years for us to implement the Thompson sampling algorithm on the hardware, but we were able to implement the Thompson sampling algorithm only for the Bernoulli distribution. So we are still struggling to implement the Thompson sampling algorithm for the Gaussian exponential distribution, because as I told you before, UCB algorithm is same for all the distribution, while the Thompson sampling has the different version for every distribution. And in the real environment, you don't know the distribution. So you need to see that how you can design the reconfigurable architecture, which learn not only the best arm, but it also learn the distribution, and so that it will reconfigure your architecture with the appropriate algorithm. And we have come up with this architecture where we are not only able to identify the arm, but we are also able to identify the which distribution, and we are able to configure the architecture. So these are the three different architectures of the Thompson sampling we have developed, and this one is the best one among them in terms of the resource one. And then I'm putting the comparison with respect to UCB, and this is very interesting comparison. You can see that the UCB algorithm, when we have the zinc with the ASIC and FPGA, UCB algorithm is much faster than the your Thompson sampling, because in the UCB you can do the arithmetic square root log calculation, and which can be done very efficiently on the FPGA. But in case of the Thompson sampling, it's a Bayesian algorithm, so you need to do the lot of random number generation and the sorting operation. So it is very difficult. But if you suppose that you are doing it for the edge devices where you don't have the FPGA, you only have the ARM processor or the ARM plus Neon co-processor, that is for the IoT devices. You can see that when you have this ARM plus Neon co-processor, Thompson sampling is much faster than the UCB, because in the ARM plus Neon processor, Thompson sampling will be able to speed up the calculations. So again, why I'm sharing this detail, because whenever you implement the algorithms, along with the algorithms, you should be able to identify what kind of architectures and the hardware it needs to be used. Okay, we have gone one step further. What we have done is that, I hope my screen is visible, or there is a black spot is there.
Sir, this notification bar is there on the right hand side.
That's it, right?
Yeah, yes, sir.
Okay. Yeah. So along with the implementation of the algorithm, you also need to demonstrate on the hardware how it works. So you can see that we have integrated these algorithms on the hardware. So you can see that this is the wireless transmitter. Sorry. So you can see that this is the wireless transmitter. This is the wireless receiver. Everything is implemented on hardware, and this wireless transmitter and receiver needs to select one of the channel, and this is done by using the multi-arm bandwidth learning algorithm. So we have a demo of this on our lab, where how the machine learning can be help you to develop the reconfigurable and the intelligent algorithms. Again, because of the time limitation, I'm not showing you the details, but if you want to know more about this, you can look at our lab website for more details. So again, I'll take a break of 1 minute. If you have any question, feel free to ask one, and then I'll start with the next version of my talk. So if you want to take a water break or something, you can take it. So we'll start in 1 minute. Okay, so if there are no questions, so let's start with the, yeah.
Sir, one of the participant, Abhiranjan, has some query. He has put in the chat box.
Okay, please elaborate. Best implement. Okay, okay, good question. So in the zinc SOC, so this is okay. Just give me 1 minute. So in the zinc SOC, this is comes from the Xilinx. There is another MP SOC and all. So this is the system on chip where you have the ARM processor and the FPGA on a single chip, and there is a AXI interface in between. So you can implement your entire algorithms on the ARM processor by using the C code, or you can implement the entire algorithm on FPGA via HDL or via HLS, or you can do the hardware software co-design where some part of your algorithm can be on the ARM processor and some part on the FPGA. And then once you implement it, you can test your power consumption, you can test your resource utilization and everything. So if you want to know more about this one, at the end of my today's lecture, I will be sharing my YouTube channel where we have shared all our labs as well as the videos of our last couple of years, where the different tutorials are there, how to develop map any algorithms on the Zinc SoC. So you can have a look at those tutorials. Also, all our papers are hardware papers have the detailed tutorials along with the source codes. So you can also have a look at that for more information. Okay, so until now, what we discussed only the single player setting, and you can see that in the single player setting, the problem is slightly easier. You just need to find out which is the best channels, and you can transmit on that channel. And you need to make sure that you don't interfere with the primary user. But the main research challenge is in the multiplayer setting, and I'm just going to discuss the challenges, and I hope the Rohit will discuss this in more detail in his talk later. So I'll keep this topic for him. Okay. So what are the additional challenges in the multiplayer multi-arm banding? Again, the same thing. You will have the K channels. You will have N users now. You can see that in the single player, you have only one users, and you will have the N users. Now you can see that these N users are the independent users. So even if you avoid the interference to the primary users, it may happen that these two users which are independent may collide with each other. So that means there will be a collision or competition among the end users. Another thing is that each user may see the channels in the same fashion. Like if the two users are very close to each other and they select the channel one, they may get the same throughput. But it may happen that if the two users are not close to each other, the throughput received on a particular channel by one user may not be same as the throughput received by the another user. So the optimal channel for one user may not be same for the optimal channel for the another user. So it's a very difficult problems are there in the multi-arm bandit one, and every year you will see that the couple of papers on this topic in the machine learning community as well as the wireless community. So you can see that instead of now having mu I, now we have the mu ij, where I indicates the index for the user and the j indicates the channel index. So players cannot communicate with each other because it's a distributed network. You need to minimize the overhead. So that is the challenge. Each player needs to take the decision independently. Number of players are also unknown. You don't know how many players are competing with me. So you need to estimate the number of players, and the number of players may change with time. So in the beginning, I may have 5 players. After some time, the first one of the player has completed the transmission. So he or she has left the network. So I need to make sure that I identify that, okay, this user has left the network. This user was using the channel, which is good for me. So I should shift to that channel. So that is the policy you need to come up. So that is another challenging problem. Then if the two secondary users select the same channel, they will collide. So they will get the 0 reward. So that means we need to make sure that I should not use the same channel as that of the secondary user. Then you can't just apply the single player algorithm directly here, because single player algorithm is designed to identify the one best arm. So if you implement that algorithm at every user is going to fix to that best term, and there will be a lot of collisions. So you can't use the algorithm as it is. And you can see that all these users are battery users. So if if the collision happens, there's a lot of battery wastage, because you need to encode, modulate, and send the data again. So that means you need to do the retransmission, and that takes a lot of energy as well as time. So you need to minimize the number of collisions. Static versus dynamic networks, that means your number of players are changing over the time, as well as channels are also changing over time. So it is called as a non-stationary channel. So for every 5 seconds or every 10 millisecond, your channel 1 was good, then channel 2 is good, channel 3 is good. So you need to learn to forget and the relearn. So that is also the challenge is there. Then you have the homogeneous channels and the heterogeneous channels. So as I discussed, homogeneous channels means for all the users, the channel statistics are same. Like for the, if the channel 1 is good for the channel user 1, channel 1 will also be good for the channel user n. So that is the homogeneous case. But the heterogeneous case is more difficult. Channel 1 may be good for the user 1, but channel 1 may not be good for the user n. So you need to make sure that each user gets the optimal channels, and there will be a lot of trade-off will be there. Okay, so you may have the optimal setting, you may have the stable setting. So for this, there are a lot of algorithms and a lot of interest in the wireless community as well as the machine learning community. So the goal is to develop the distributed algorithm to maximize the expected sum rate. So this is the same as the single player, but you need to make the collision less. You need to minimize the number of collisions. So that is one of the very interesting and fascinating problem in the machine learning community as well as the wireless community. And this is the glimpse of the some of the work which has been done in this domain. And you will see that the lot of good quality conferences as well as the journal papers, they have the papers significant contributions in this domain. And they again, you can't solve all the problems in one domain. Sometime in the beginning they started with the known user case, that the number of users are known, and the static case where the channels remain stationary and the number of users are not changing with time. Then they went to the unknown case where the number of users are unknown. Then they went to the dynamic case where the number of users are changing with time. Then they went to the non-stationary case where the channels are changing with the time. Then the people are addressing the problem where your user doesn't have the sensing capability. So you can't sense the channel, you can only transmit the channel for the, especially for the IoT user. And it's a lot of open research problems are there in this domain, and it's one of the good domain to explore even today. Okay. So if you want to know, if you are really interested in this domain, if you want to know more about this domain, then you can look into the one of our detailed tutorial which we gave in the CompsNet conference in 2021. This is I did with my collaborator from IIT Bombay, Manjesh, and it's a 3.5 hour tutorial where we explain the each and every part of the multi-arm bandit for single player as well as multiplayer in more detail. So if you want to know more about this, you can look at these papers, you can look at the corresponding research papers on our website, and there are additional videos are there on our YouTube channels. You can look into that corresponding YouTube channels if you are interested in this domain. Okay, so again, I try to keep the discussion on the multiplayer as limited as possible, because Rohit will take care of this, and it's again emerging research problem. So only for the people who are interested should be aware about this one. So that's why I kept the discussion limited. Now we have completed this till multiplayer, and even in this there are so many open research problem, and there are additional open research problem which I would like to share with you, which is related to the multiplayer multi-arm bandit. And this includes the one problem which recently we are working on. So you can see that till now what we have discussed, our transmitter selects the channel, transmit the data to the receiver sends the feedback. You use that feedback as an information, and it will help you to select the channel in the next time slot. So this is the conventional model. But in the if you look at into the how the wireless system works, you may have the additional information along with the throughput, which will help you to better decision making. For example, in the wireless network, now you will see that there are heterogeneous network. You have the main base station, then you have the pico base stations, which are connected via fiber network to the main base station, and then you inside the your home you may have the Wi-Fi network, Bluetooth network, and because of the deployment of your cellular spectrum in the shared and the license spectrum, the user, which is the cellular spectrum, may get the interference from the adjacent channels. So this interference can be measurable, this interference cannot be measurable. So if such interference is measurable, then can we use of this measurable interference to improve the performance? For example, there is a TX, there is a RX, you are transmitting on say channel 1, and you know that there is a interference, there is another base station say interference, which is also transmitting on the channel 1. So can you make use of this knowledge to do the better decision at the transmission? So this is called as incorporating the supplementary information in your learning algorithm. And recently we did this study for the LTE transmitter. So what we did is that we implemented the LTE transmitter and the receiver as per their 3GPP standards. So this is the transmitter. You can see that there is all the physical layer is there. And in LTE transmitter, what happens that on the downlink, the base station transmit the data, then the user terminal performs some measurement like the SINR measurement. Then in case of the rank, in case of the MIMO system, it performs the rank indication and other measurement, and it sends that information back to the transmitter over the uplink. So this is the information we can make use of it in the conventional wireless network. But in addition, can we make use of this interference information which is available at the transmitter to make a better decision? And in our paper, we showed that by using this additional supplementary information, you can improve the performance of your system, especially the BER and the throughput performance of the system. So if you want to know more about this, we are presenting this work in the CompsNet 2022 in the first week of January, and the corresponding videos will be available on our YouTube channel in the next couple of weeks. So if you want to know more about this, and if you are interested, you can look at into this paper. Okay. So this is the one research problem, which is how you can make use of the supplementary information. Then how to make use of the subset selection. For example, right now we are assuming that one user is selecting the one channel only. What happens when the one user wants to select the multiple channel, like carrier aggregation in the LTE or 5G? So these are the problems are there. Then in the massive MIMO, in case of the joint radar communication system, in case of the reflecting intelligent surfaces, especially with the beam forming, how to select the appropriate beam, how to learn the beam. Everywhere you can use these bandit algorithms as well as the reinforcement learning algorithm. And if you are from the circuits domain, hardware domain, then how this algorithm can be mapped into the reconfigurable architecture. Because machine learning community will not be interested in the hardware mapping of this algorithm. Only the wireless or the people who works in the robotics and IoT will be interested in this one. So again, this is a very good domain you can explore, where efficient implementation of these algorithms on the hardware one. Okay. So this completes my discussion about the multi-arm bandit algorithms or the learning algorithms and how they can be used in the wireless network. If you have any doubts, please feel free to ask me now. Otherwise, I'll take 5 more minutes to explain some of the other works which we are doing in our research lab and give you some videos, small videos to show how we are demonstrating our work. So any doubt, any question from the audience? Okay. So if there are no questions, so I'll quickly wrap up it in the next 4 or 5 minutes. So if there are any discussion or something at the end, we can do it, or we can have the early lunch. So in our lab, the name of our lab is Algorithms to Architecture. So that means that the students not only has to work on the simulation part of the research, but they need to demonstrate their everything on their hardware or the lab prototypes. So that is a very critical part of any students who work with us, that just a theoretical work is not sufficient. You need to develop, you need to demonstrate in the real world setup. And because of this philosophy, we have got a lot of advantages, that we were able to develop multiple demonstration during our last 4 to 5 years. So one such demonstration is this test bed using the USRP. So the first work which I discussed about the multi-arm bandit for the single and multiplayer setting, this we developed at IIIT Delhi. We developed the demo where you have the transmitter and you have the receiver, and you can transmit the corresponding. You can use the machine learning algorithm to demonstrate in the real RF work. And this demo got the best demo award in the CrownCom 2016. Then along with the multi-arm bandit, we also worked in the multiple wireless algorithms. First, one of the work is the wideband spectrum sensing, and in this work we were able to develop the demonstration in a collaboration with the University of Luxembourg. So this work was done by one of my PhD student. So here in this work, I'll just not show the entire one, but here you can see that we have developed the complete multi-USRP based system using for the direction of arrival estimation. And I'll just show you how the entire system looks like. So in the direction of arrival, because in the 5G and 6G, you will have the DOA. So you will have to estimate the direction of arrival in the real time. So your spectrum sensing should be in the time, frequency, as well as spatial domain. So you can see that these are the horn antenna which transmit in a particular beam direction. This is the transmitter, and then this transmitter is transmitting the data, and then you can see that this is the multi-antenna receiver. Again, we have used the spatial antenna so that in between some antenna are missing, and by using the signal processing we can reconstruct the data from the rest of the antenna. So this is the multi-USRP receiver which receives the data from the multiple antenna, process the data, and then the processed data you find out the DOA, and the DOA is being display. This is the server where the processing is takes place, and you can see that the real-time DOA estimation takes place. So you can see that by using the such demonstration, this demonstration has been done at the IEEE ICASP as well as IEEE 5G forum. So with the demonstration, we are able to demonstrate our algorithms on the real RF environment. So again, it needs a lot of hardware, but at the end, this is very important for any research lab. So then recently, there is a lot of talk about the edge devices or edge AI, or how to implement the deep learning algorithms on the microcontrollers. So one of our work in collaboration with the ST Microelectronics in Italy as well as the Noida, we have developed the neural network based DOI estimation on the microcontroller. So you can see the microcontroller has very limited memory, so you need to develop a very small scale deep learning algorithm. And this work got the best paper award in the application oriented research category in the AI/ML system 2021 conference. Again, this conference is started by the CompsNet and usually organized by the IISc every year. So this is another work where we have done the complete GUI and the demonstration on the microcontroller in the real time. Again, if you want to watch the video, the complete 1 hour video is there on our YouTube channel. Then sometimes you may have the better hardware than the microcontroller. For example, you may have the Zinc SoC or the FPGA. So we have also implemented the deep learning algorithms for the DOA estimation on the SoC. So the corresponding video is also there. So what I would like to show you is the final demonstration. So this demonstration is on the real time on the SD SoC, which is on the Zinc SoC, which has the FPGA and ARM processor. So we have deployed the Linux on the ARM processor, and we have developed the application, and the algorithms, deep learning algorithms works on the SoC. And this is again, you can see that the wideband spectrum sensing, where you can use the subnequist sampling and then the deep learning algorithm to identify the status of the frequency band in the real time. So now the boards are being configured. And then once the boards are configured, we run this GUI, which captures the data from the board, and you can see that the here the predicted and the actual band are shown along with the accuracy, like what is the accuracy of the predicting the band. So as you get more and more samples, your accuracy parts gets better. So we have tested it for the different SNRs and all those things, and hopefully in the week or two, the corresponding paper will be online. But this video is already there on the online if you want to know. Okay, so again, the aim of showing this one is that you need to think about how you can, if you are faculty, you need to think about how you can develop the prototype along with the conventional simulation result. It's very important for the today's world where your industry, you want to make the impactful research for the industry. So this is another air to ground communication test bed. Again, this work is done by my PhD student Niharika. So this work also got the best paper award in IIIT CS in 2017. Again, we have developed the algorithms and then we have demonstrated it using the USRP based setup. So this is one of the work. Again, the details are available on our website. This is the work which is going on right now in our lab, how to design the intelligent and the reconfigurable physical layer. So there are two sponsored projects, one from the DST, one from the METI, one for the wireless communication, one for the joint radar and communication receiver. So if you are interested in this domain and if you want to do the research, feel free to contact me. But again, we expect the student to spend at least 6 to more months in this domain for any productive research work. So this is all about the research work. Now, if you want to train or understand how these things are done, on our YouTube channel, I have made all the videos, lab videos public. But if you are a teacher, if you want to get access to the lecture videos, those are also can be shared if you are interested in this domain. So I teach the embedded logic design and advanced embedded logic design courses at IIIT Delhi. It has the lab component as well as the theory component. So if you are interested, you can have a look at this video. Then whatever the student develop, because this is the course where student develop the video game on the FPGA. So the corresponding videos are also available if you want to know more. In addition, we also organize different outreach activities. For example, this is the 5-week VLSI revisited course, which we organize, we are organized for the last 2 years. This year we had 180 participants, out of which almost 40 were from the industry, and it's a 5-week course, and it is planned just before the placement season, so that you can revise your concept for the VLSI industry. So every year it is organized in the June or July frame. So feel free to be a part of this program. It's a very good program. I usually enjoy teaching in this program, and we are trying to make it bigger. It is supported now the IEEE CA Circuit and System Society as well. Then we also organize different workshops. So keep on looking at our website for the multiple workshops. Next month, in the second week of January, I'm organizing a 5-day faculty development program on the AI on SoC. So how to deploy the AI algorithms on the system on chip. Again, this is the IICT sponsored workshop. You will get the IICT certificate if you complete the course and pass the exam, and if you attend all the lectures. So that is the 5-day workshop, and we have the speakers from ST Microelectronics, we have from Xilinx, we have from IIIT Delhi, and we are looking for some more speakers from the Cadence as well as the Intel. So if you are interested, feel free to look at. And sometimes we also organize the full FPGA program, where participants develop the video game during our 5-day course. So we are planning usually in the next December timeline, we usually plan this kind of FDP. So if you are interested, feel free to approach us for this kind of activities. Okay. So with this, I am done with today's session. Just in time, I have taken a couple of minutes extra, but I think that is fine. So if you have any doubt, anything you want to ask, feel free to ask me now.
Yes, so now session is open for the participants. All are welcome to ask your queries if you have some. in future also, if you have any query, you can refer to the website of sir. So from there you can email him and get send your query, right? Okay, so if you don't have any query, then we will stop the session over here only, and our next session will start at 2 p.m. where our speaker from IIT Hyderabad, Dr. Vinod Kumar, and just before after this, we will share the feedback form with you, which you can submit, right? So this is the last call I'm asking from the participants if you have any query. Otherwise, we will bind up the session. Okay, so if you don't have any query, then we thank you. Sorry, I think there was a yeah. So I will say once again thank you to sir for giving his precious time to be as a speaker in the this faculty development program, and hope all of you must have get benefited out of it. And then thank you so much, sir, once again.
Okay, thank you. All the
Thank
best.
you. See you all the participants in the next session. Thank you so much. Signing off from here. Thank you.